Alright, so this is a ninth video in the series of name reactions, and today we are going to discuss about Bergman and Meyer's cyclization. But before we jump into the reaction, its mechanism and some practice problems, we need to discuss some basics. So whenever you see a bond between two atoms, we need to know that we have a pair of electrons between them. So a bond represents two electrons. Whenever you see tin hydride in your reaction as one of the reagent, you need to think about radical chemistry, because tin hydride dissociates into tin radical and a hydrogen radical. In this Bergman and Meyer cyclization, you are most likely to form a aromatic ring. So basically, you are forming a cyclized product. That's why the name is given as cyclization. In Bergman cyclization, you will have alkyne as one of your reactant, whereas in Meyer's cyclization, you will have allene as one of your reactant. So these are some basics we need to know before we start with Bergman and Meyer cyclization. So now we know all these basics, so let's go ahead and understand the reaction, its mechanism, and some practice problems. Okay, so suppose I have this particular starting material. Right? We have a alkyne, alkene, and an alkyne. And I'm giving heat it, or I'm shining a light on it. So what is the mechanism? So here we are able to see the alkyne group. So this is a Bergman cyclization. So what is the mechanism? When you fall light on it, or when you provide heat to this system, this alkyne bond will cleave. So a single bond contains two electrons. So let's cleave this bond and give two electrons here, similarly here. Right? So we have two electrons here, two electrons here. Basically, I am representing one bond with two electrons. Now, once you have this, cyclization is going to happen. So let's number the carbons. 1, 2, 3, 4, 5, 6. If these two electrons come closer and form a bond, we will have a 6-membered ring. If these two electrons come closer and form a bond, we have a 4-membered ring. And 6-membered ring will be preferred over 4-membered ring. So that's why the electron present at carbon number 1 will come closer with the electrons, one of the electron present at carbon number 6, and will form a bond. So this will give me so let's number them. So this is 1, 2, 3, 4, 5, and 6. So now we have a bond between 1 and 6, two electrons coming closer and forming a bond. And we have a radical at carbon number 2 and radical at carbon number 5. So this intermediate we have generated by shining a light on this particular alkyne. So mechanism is simple. I have just represented these electrons here. I connected two electrons and formed a 6-membered ring where electrons are present at 2 and 5. So now we have this. So suppose I have this particular system which I have recently generated, and I'm reacting this with tin hydride. Okay, so I have this particular tin hydride. So tin hydride can be written as this one. Okay, so this electron will come closer. This bond is made up of two electrons. One of the electron will be used to form bond with this electron, and another electron will fall on tin radical. Similarly, here also, this electron will come closer, form a bond with this particular electron, and this electron falls on tin. So you have a benzene ring now. We have formed a CH bond, and this whole represents a benzene ring. For example, suppose I have, instead of tin hydride, I am reacting this particular intermediate with, instead of hydrogen I am taking this deuterium. So mechanism is same. This electron come closer, this bond is made up of two electrons. One of the electron will form bond with this electron and another electron will fall on tin. Once again, same chemistry with this radical, and this will give me deuterium here and here. Okay, so let's recall what we did. So we have alkyne, this triple bond, one of the bond I represented in electron fashion. Then 6-membered cyclization happened and we get this particular radical intermediate. When you react this radical intermediate with tin hydride, you get a benzene. And by changing hydrogen with deuterium, you can substitute your hydrogen with deuterium. So this was the Bergman cyclization and the mechanism involved in it. Let's see the same reaction but with some different reagent. Okay, so we have this particular alkyne, like the previous question. I'm shining light on it or giving heat to the system. So this single bond contains 2 electrons. This single bond contains 2 electrons. So we have 2 electrons here and 2 electrons here. Okay. Now these 2 electrons come closer, form a bond, and we have a 6-membered ring. Let's number them. So we have formed this particular 6-membered ring. So this is 1, 2 contains radical, 3, 4, 5 contains radical, and now we have a bond between 1 and 6. Correct? So I just formed a bond between 1 and 6 by using 2 electrons and we have a bond. And these 2 radicals are still at 2 and 5. Okay. So we know when we react this one with tin hydride, we get a benzene. If we react it with deuterated version, we get deuterium atom at 2 and 5. But if I react this with this particular diene, what do you think? What is going to happen if I react this particular intermediate with this particular diene? Feel free to pause the video and try the mechanism. What could happen if I react this radical with this diene? Okay, so we have a hydrogen here, right? Now what can happen is this electron can come closer. This bond contains 2 electrons. One of the electron can be used to form bond with this radical and another radical can fall on this carbon. So we have we have still a radical here and we attached hydrogen here. And now what is this? This has converted into the following. We have a radical here, we have a double bond here, and now we have these 2. Correct? Now at this point of time, what is going to happen is this radical can come closer and this double bond contains 2 electrons. So one of the electron can form bond here and another electron can fall on this carbon. So this will give me we have still a double bond here. Now we form double bond here and we have electron here. Correct? So now these 2 is going to react. So let me redraw them again. So this is, I'm writing here once again. Okay, we have a radical here and a hydrogen here. I just flipped it. This hydrogen is below, up, this electron up, below. So just same thing, I just flipped it. And we have this particular system. I have drawn the exact same thing, correct? Now what can happen is we have a hydrogen here. So this radical can come closer. This bond contains 2 electrons. One of them will be used to form bond here, and this another electron will fall here, and this electron falls here to form double bond here. So this will give me, so we have a benzene, and now this is also converted into a benzene. We have a double bond here. So this is the mechanism. When you use this particular diene, you will get 2 benzene. One benzene coming out of your starting material and one benzene coming out of your reagent. So let's recall once again the mechanism about what we did. So we had alkyne, one of the triple bond I represented in electron fashion. I cyclized from center 1 and 6 and we got this intermediate. Now we used this particular diene. These electrons take this proton and generate 1 electron here. Now this can rearrange to give this one, and then these 2 can combine to give me this 2 benzene. So let's conclude what we did till now in a separate piece of paper. So we start with this particular alkyne, okay, and when I give heat to it or maybe light to it, this gives me this particular intermediate. Correct? And now if I react this with tin hydride, excuse me, right? Basically I'm using tin hydride bond, then this will give me a benzene ring, and these radicals have taken hydrogen. If I react it with, instead of hydrogen, if I take deuterium, we have deuterium atom here. If I react this intermediate with this particular diene, we have 2 benzene as a product. 1 benzene coming out of this intermediate and 1 benzene coming out of this reagent. So this is the conclusion so far. This is what we call the Bergman cyclization, where you are cyclizing and forming this product, the cyclized product. And we have also seen the mechanism for each step. Now let me give you the short trick to immediately find out the product. So suppose I have the same starting material and I want to quickly draw the product. So what is the short trick we can use? So whenever you see such kind of system, you need to spot your alkyne. So I can see 2 alkynes in my system. So once you find out the alkyne, all you have to do is connect their terminal part. So this is my terminal part and this is my terminal part. So all I need to do is connect them. And you need to convert this triple bond into double bond. So 2 things you have to remember. 3 things you have to remember. The first thing, find out your alkyne in the system. Once you find out them, second thing, connect the terminal part. And the third thing, convert your alkyne into alkene. So let's do it. So I have spotted my alkyne. The first part I have completed. Second part, I have to connect this terminal part. So let's number them. 1, 2, 3, 4, 5, 6. Okay, so this is 1, 2, 3, 4, 5 and 6. So between 1 and 2, the third part, you have to convert this alkyne into alkene. So this is my double bond, this is my double bond, and this is my double bond, and this is the product. So 3 things you have to remember. Find out the alkynes, connect the terminal part, and convert alkyne into alkene, and you will get your product in just few minutes. Okay, let's solve some practice problems. So this time I'm using my starting material, something like this. So this is my starting material. I'm heating this reaction by using DMSO as solvent at 180 degrees Celsius using this particular diene. So what is the product and what is the mechanism? So pause the video, draw the mechanism and find out the product. You can also use the short trick to immediately form the product. So let's go ahead and do it. So the first step, we have 3 steps. The first step, find alkynes. Second, connect terminal part to form 6-membered ring. And the third thing, convert your alkyne into a alkene. That's all you have to do. So this is my alkyne and this is my alkyne, correct? So if I connect them from here, it will give me a 6-membered ring. 1, 2, 3, 4, 5 and 6. And I need to convert this triple bond into double bond and the product will be here. So the product I can write. So the product is, so let's draw the 6-membered ring first. So this is 1, 2, 3, 4, 5 and 6. Now from 1 and 6 we have a CH2 and a sulfur, correct? We have from 6 we have a CH2 and sulfur. Now these two are connected by a alkene and rest will be same. This is sulfur. So this is the product for this reaction. All I did, spotted my alkyne, connected terminal part to form a 6-membered ring and converted this triple bond into double bond and rest will be the same. And this is the product. Let's solve one more practice problem. Okay, so this time we have a pyrrole containing starting material. Okay, this one is methyl. Then we have okay, so this is my starting material, shining light on it and using THF as a solvent, find out the product. Use my short trick to immediately find out the product. Okay, so step 1, find out the alkyne. Alkyne, alkyne. Point number 2, connect alkyne in such a way that you form a 6-membered ring. So let's number 1, 2, 3, 4 and 5 and 6. If I connect my alkyne from 1 and 6, I will form a 6-membered ring. And the third part, convert your alkyne into alkene and you are done. So let's draw the product. So this part will be same. We have a 6-membered ring now. So this is my 1, 2, 3, 4, 5 and 6. 1 and 6 connected, triple bond converted into a double bond, right? And then lastly, all you have to do is rest part will be same. So this is A, B, C, D and E. So we are forming 1, 2, 3, 4, 5, 6, 7-membered ring. So this is A, B, C, D and E. So this is the product for this particular reaction. So this is about the Bergman cyclization where we have alkyne as our starting material. Let's see the Meyer's cyclization, its mechanism, where we have allene as our starting material. Okay, let's discuss the Meyer's cyclization. So in Meyer's cyclization, we have allene in our starting material, right? This time we will have allene. So let me draw the starting material. We have a triple bond here. Excuse me. Ignore this, okay? This is not a radical. I just, by mistake, I drew it. So we are still going to form a 6-membered ring in Meyer cyclization. So we have an alkyne here and we have an allene part here. Okay. We have an allene part here and we have an alkyne. So this is a Meyer cyclization. And we are still going to form a 6-membered ring. So let's number. This is 1, 2, 3, 4, 5, and this carbon right here is a 6. So we have some idea that these two are going to be connected. Okay. So let's draw the mechanism when a light falls on it. So when a light falls on it, this triple bond, so we have a single bond here which represents 2 electrons. And we have an allene, right? So this is my one of the bond of the allene. Here we have a carbon. And this single bond I'm representing in 2 electrons. Let me write carbon here. Okay. So I converted this single bond into 2 electrons and this particular single bond of allene into 2 electrons. Now we need to cyclize this one in a 6-membered ring fashion. So 1, 2, 3, 4, 5 and 6. So this radical present at 6 carbon will be connected with the radical of carbon number 1, so that we will get a 6-membered ring. So we have, so let's say this is 1, this is my 2 which has a radical, and we have a double bond here. This is 3 doubly bonded to 4, this is 5 doubly bonded with 6, and we have a CH2 radical. So this is my 6. 6 has this, we have a C carbon here which is present here. So this is CH2 radical. So this time we have generated this particular intermediate. We have a radical here and we have a radical here. So this is what we call the Meyer cyclization, and this is what the intermediate is. Correct? And if I add tin hydride this, okay, if I add this tin hydride, I will get the toluene as my product. Simply just give hydrogen to your radicals, because we have used tin hydride which will give me H radical. Okay, so these two will combine and will attach hydrogen at the respective center. So this is the product. So this is what we call the Meyer cyclization. If in case if I use the deuterium atom instead of hydrogen, here will be deuterium and one deuterium will be here. So the product will be CH2D. So this is what we call the Meyer cyclization. You need to spot your alkyne and allene. As soon as you see the allene, you know it's a Meyer cyclization. And still you are going to form a 6-membered ring. Correct? So for that matter, when I shine light on it, one of the bond out of alkene will be converted into radical form. And this particular, the outer part of allene will be converted into radical. The radical present at carbon number 1 and 6 will cyclize to give me this one. So this is the intermediate. And if I use tin hydride, the respective position will get hydrogen. If I use the deuterium instead of hydrogen, the respective position will get deuterium. So this is what we call the Meyer cyclization. Okay, so here's one question based on Meyer cyclization for you. So I have a benzene. Then we have this one. We have this represent carbon of allene. Okay. Okay. So this is my starting material. Giving light to it, what is the product? So to find out the product, first we need to understand whether it is a Bergman cyclization or a Meyer cyclization. So in a Bergman cyclization, you will have two alkynes. But in a Meyer cyclization, you will have one alkyne and one allene. Okay, so this is for Bergman and this is for the Meyer cyclization. So I can see one alkyne and one allene. So this is a Meyer's cyclization. And we are still going to form a 6-membered ring. So let's number starting from alkyne. So this is 1, 2, 3, 4, 5, and this center carbon of allene is carbon number 6. So let's connect 1 and 6 to form a 6-membered ring. That is what we want. So let's connect them. Okay, and convert this triple bond into a double bond, and this double bond will be saturated. So let's form 6-membered ring. So this is my benzene. This is the newly generated benzene. So this is 1, 2, double bond will be here, 3, 4, this is 5, and this is 6. Excuse me, we should not convert this double bond into a single bond, because when we have seen the mechanism, this double bond is intact and we are breaking this double bond, right? So this double bond will be intact and we will still have a double bond here. And this part will be same. So this is my 1, 2, 3, 4, 5, 6. We are forming another 6-membered ring. Okay, and here we have a radical that will be taken by, let's use the tin hydride. So here we will have a hydrogen. If someone asks you what is the intermediate for this particular reagent, then it will look like this one. Okay, so basically the radical version you have to show. So I have one radical here and one radical right here. So this is the intermediate for this reaction, and the mechanism I have discussed in the previous page. So that's it for the Bergman and Meyer cyclization, how to differentiate between them, what is the mechanism, which reagents you can use, the mechanism, and short trick to find out the product. So that's it, and thank you for watching. Do subscribe.